Hello. In previous videos on Unit 7, we were able to take chemical formulas and predict the structure, the Lewis structure, predict the shape that comes with the bond angles, and predict whether that molecule is polar or nonpolar. We're going to take these predictive powers a little bit further, and we're going to predict whether one molecule has a higher or lower boiling point or melting point than another using geometry, using polarity, and in this video we'll introduce intermolecular forces. Okay. Intermolecular forces. I have a couple of definitions. Due to molecular polarity, which we had talked about in a previous video, where we answered the question, is a molecule polar or nonpolar? By knowing this answer, we can predict what type of attractive forces can occur, and attractive forces are between molecules, different molecules, or possibly different atoms. Those are called intermolecular forces, or simply IMF, or IMFs. And the four types of IMF that I will discuss in this video are listed here. And the first one is dispersion. Oh, I should mention that these are in order of strengths. So this is the weakest. And this is the strongest. We won't get too much into it in this video, but sure, if a molecule has many weak interactions, those might actually be stronger in aggregate compared to a molecule that only has one or two of these stronger interactions. So yeah, the amount of the interactions also affects the strength of how these molecules you could think of stick together. Let's take a look at our first IMF. It's called dispersion. Another way people know this is London forces. Some people think of dispersion, or better visualize dispersion, as induced dipole as well. Induced dipole IMF. Okay. So we'll work with A first, dispersion. Throughout this video, I'm going to reserve the color pink for phrases or concepts that I really want to understand well and keep in mind as I work through an exam. And the first one I'm going to put here is that nonpolar molecules have dispersion forces have only, that's the main word, have only dispersion forces. Oh, what else? Nonpolar molecules have only dispersion forces. Oh, even if it contains polar covalent bonds. So that's kind of weird. The molecule has polar covalent bonds, but if the molecule is symmetrical and those dipoles cancel out, the molecule is nonpolar, and nonpolar molecules only have dispersion forces. And so what's a dispersion force? Like I said, you could think of this as induced dipole. And let's take a molecule that is definitely nonpolar. Let's take Cl2 gas. Draw the Lewis structure. And because that bond is a nonpolar covalent bond, the electrons are shared equally, and you don't have a dipole. There is no dipole, so there is no imbalance of electrons between these two chlorines. Our conclusion from a previous video, and you should know how to do this, is that this is nonpolar. But what is a dispersion force? Every now and then, if you can freeze the molecule and look at its partial charges instantaneously, yeah, at some point there may be an imbalance and you'll have a partial negative here and a partial positive here. So a dipole towards the chlorine on the right. Remember, this can also be called induced dipole, and a neighboring molecule can induce a molecule to have an induced dipole. And the molecule on the left is inducing the molecule on the right to have these electrons push towards the chlorine on the right. Okay? And you'll have, as typical, or as you know, opposites attract. So an IMF is an attractive force. This is a dispersion IMF. Okay? Again, the molecule is nonpolar. And the bond itself is a nonpolar covalent. That typically is easy to understand. I just want to warn you, if you're given a molecule that has polar bonds, let's take CF4. So I'm not drawing it in 3 dimensions. I'm not worried that this is tetrahedral or not. Well, I should know it's tetrahedral because having it be tetrahedral, even though we have bond dipoles, this molecule is nonpolar because the dipoles cancel out. CF4, my conclusion here is CF4 only has dispersion forces, even though it has polar covalent bonds. And again, that is our first pink phrase here. Okay, let me talk about trends now. Because the title of this video has melting point and boiling point. So we're going to want to know, how do these IMF affect those properties? Let me give you some data. We have F2, Cl2, Br2, and I2. We are going down the halogens, and the halogens are diatomic. Let's just take a look at the boiling points for these elements. These are molecular elements, right? And we have negative 188. All of this will be in degrees C. Negative 34, 59, and 184. So the boiling points go up. All right. The boiling points go up because of size. So here's another phrase that I want to remember. As increased size, I should say the number, or should I say the number or the strength? The number and or strength of the dispersion force increases. Thus, increasing the boiling point and the melting point. Okay. If room temperature is RT equals 25 degrees C, it's a little bit toasty, but I live in the south, so it's easy to get to 25 degrees C in the summer. What are the states of each of these diatomic elements? Well, at minus 188, if that's the boiling point, right, At room temperature, we are above the boiling point. Therefore, this is a gas. 25 is above negative 34. It is a gas. Chlorine is a gas. But here, the boiling point is 59 for bromine. And at 25 degrees, we had not reached the boiling point yet. This is a liquid. And this one, see, I don't have any data for the melting point, but at room temperature, we had not reached the melting point yet. This is a solid. Okay. Now, why is this the case? Let's take a look at I2. I2 is a large atom or large molecule, and you have two iodines like this, versus a fluorine, which are pretty tiny, and we have diatomic fluorine that might look like that. The bigger the molecule, the more chances that you'll have an induced dipole, or we could call this a temporary dipole. I should have mentioned that earlier. Temporary. Oops. Oh man. I can't make any mistakes now. I can't find my whiteout. Temporary dipole. Okay. And these are much smaller. Another way you could say is that the bigger the molecule, the more polarizable. More chances that you can have a temporary dipole. Okay. Let's see. Do I want to do any other example? No, I think I'm good with this. Let me just remind you though, we do have noble gases and they're single elements. So even when you have a single element and there's no bond, therefore you cannot have any bond dipoles, you can still have an induced dipole. Okay? Because for instance, xenon is a big noble gas versus a neon, a smaller one. Again, you could have imbalance of electrons on different sides of the atom. So yeah, you could have a temporary dipole that looks like this that can induce a dipole on a neighboring xenon atom. And then hence, the bigger the atom, also the more chances that you could have this imbalance. Okay, and the more likely you'll have a bigger imbalance. All right, more polarizable because it's bigger. And some people like to say it has a bigger electron cloud. Okay. We've had two phrases so far that are in pink. Let me give you a third one before we get to the next IMF. And that is all molecules and atoms display or have dispersion forces. And if it's nonpolar, remember that the only IMF is dispersion forces. IMF dispersion forces. Okay, let us move on to B. B is, where'd my paper go? B is, here it is, dipole-dipole. And these are now, to differentiate, while dispersions are induced dipole, dipole-dipole, we'll call them permanent dipoles. But these are permanent dipoles on polar molecules. Because again, nonpolar molecules will only show dispersion. That's a huge distinction. And actually, it's a common mistake. It's a common mistake to think that this molecule has dipole-dipole interactions. It has no dipole-dipole interactions because CF4 is nonpolar. Okay. So let's take a look at dipole-dipole, and we're going to pick a molecule that has polar bonds. And the molecule is polar. So let's take sulfur. Okay, how about this? Sulfur. And we have F. So that's a very polar bond. And I'll put another F here. Fill in your lone pairs. Okay. F is electronegative. That's a phrase that you should have known from a previous video, and I'll put it here. F is the most electronegative atom. And remember oxygen? Oxygen is second most. That's phrase number 4. These are permanent dipoles, so they're not induced, and we have a neighboring molecule that has a sulfur that is always partial positive. I'm not going to draw the lone pairs in this case. And we have a dipole-dipole interaction. As simple as that. Another example is, let's take a carbon-oxygen double bond, and I'll fill in the lone pairs in this case. Okay. Well, oxygen is very electronegative. We'll make that partial negative, which renders the carbon partial positive. Again, another way you could show this is that you have a bond dipole like this, okay? But also, and I should have mentioned it for SF2, only polar molecules can have dipole-dipole interactions. So if it's nonpolar, again, go back to dispersion and say that nonpolar molecules only have dispersion forces. How would you draw a dipole-dipole interaction in this case? You have to line up the partial positives to the partial negatives. And we have this. Right? That is dipole-dipole. Next, hydrogen bonding. Hydrogen bonding is the third IMF, but technically, and I'll write it here, technically it's a subset of dipole-dipole. So most textbooks still set this apart and call it a separate category, but it is a specific type of dipole-dipole. And if you have a molecule that displays hydrogen bonding, you say hydrogen bonding. You don't say special dipole-dipole or dipole-dipole. So it's a specific type of dipole-dipole. This letter C, hydrogen bonding. Now the definition can be a little bit wordy because it's very specific, dipole-dipole interaction. And a hydrogen bond occurs between a hydrogen that's covalently bonded to O, I should have put this in order, to N, O, and F. Those 3 atoms. And then you take that hydrogen that's covalently bonded to N, O, or F, and it intermolecularly bonds to another N, O, and F. So how do I want to say this? Hydrogen bonds. No. Hydrogen bond occurs between a hydrogen that is covalently bonded to N, O, and F, and So it's between that hydrogen and another N, O, or F. Okay. Let us take water. Water we know is very polar because oxygen is very electronegative. And we're going to show a hydrogen bond. So hydrogen bond is this hydrogen that's connected to an N, O, or F, having an IMF, intermolecular force, with N, O, or F. So this is a hydrogen bond. I think to avoid careless errors, we should look at some molecules that some people think there's a hydrogen bond, but there really isn't. It doesn't fit the definition. And that is if you don't have an oxygen, nitrogen, or fluorine. So something like this is not a hydrogen bond. What do you want to call this? This is just a run-of-the-mill dipole-dipole interaction. It's dipole-dipole. Okay. Another thing that I want to mention is that when you have a hydrogen bond, you have two partners. You have what's called the hydrogen bond donor. It's the molecule that has the hydrogen covalently attached. Hydrogen bond donor. And here we have the hydrogen bond acceptor. Okay. One last thing, and I sometimes make this mistake, but what if we had water, and we're gonna have two different molecules here. What if we had water, and I'm making a supposed hydrogen bond? So the donor satisfies the definition so far. It's a hydrogen covalently bonded to O, N, or F, and I bond it to an electronegative atom, such as chlorine. And let me make this polar, sorry. So we'll put H's here. Is this a hydrogen bond? We do have a chlorine that's partial negative. We do have a hydrogen that's partial positive. The hydrogen is covalently bonded to oxygen. But the fact is, since the IMF is between hydrogen and a chlorine and not a nitrogen, oxygen, or fluorine, you will know this as just a dipole-dipole interaction. Okay. Now, let me give you one more example, and that example is this one here. What if I have this molecule? This is methanol. Okay, this is methanol. If I ask what IMF this molecule displays, I would say it has dispersion forces because all molecules show dispersion. Okay, and it will have hydrogen bonding, and we'll draw that in just a bit. But it also has dipole-dipole. So it has an interaction that is not hydrogen bonding and not dispersion. Let me show you the easy one. Let's show you the hydrogen bonding one. So the hydrogen bonding is just simply this, where the hydrogen that's covalently bonded to an O, N, or F has an interaction between an O or between an N, O, or F. That's hydrogen bonding. So where is the dipole-dipole? The dipole-dipole could be something like this, because we know that carbon is partial positive, because oxygen is pulling electron density away from it. So we could have this dipole-dipole interaction, O, H, then we have this other molecule, this is methanol. You may not know that name. It's a type of alcohol. But isn't this a dipole-dipole interaction? Right? We have permanent dipoles, and we're showing the attraction between opposite charges, partial negative and partial positive. This is called a dipole-dipole. I'm not going to illustrate dispersion, but we have, how can I just explain this? Well, all molecules have dispersion forces. So while this carbon-hydrogen bond is nonpolar, due to temporary dipoles, the hydrogen can be positive or can be negative, and that will induce a neighboring molecule to have possibly a hydrogen that is the opposite charge. Okay, so let's say this. So I know that this carbon is partial positive, but that would make this hydrogen less partial negative. Let's say it's in temporary. Well, a neighboring hydrogen on a different molecule could be rendered partial negative. Oh, sorry, partial positive. And that's the induced dipole. So we could call this dispersion. All right, so I ended up drawing you an example of dispersion. It gets a little bit complicated. You want to be able to look at a molecule and see. Every molecule has dispersion forces. You probably want to check whether there's a possibility of hydrogen bonding and a possibility of dipole-dipole that is not hydrogen bonding. The last one is ion dipole. An ion dipole is the strongest, okay? And it's very easy. If you have sodium chloride and it's solid and you throw it into water, you're actually going to dissolve this into its ions. And the way that chemists indicate that is by putting AQ for aqueous. Cl minus aqueous. An ion dipole IMF looks like this. You have one ion, and you have one molecule that has a permanent dipole. In this case, we'll have water. Now you just have to match opposites attract. We know we have a permanent dipole between oxygen and hydrogen. So opposites attract. There's your ion, and there's your oxygen that's part of a dipole bond. The interesting thing about this is that water will surround sodium via IMF interactions with the oxygen, and it will form like a cage. Chlorine, Cl minus, will be the opposite. It will be more attracted to the hydrogen. And same thing, you'll have a cage. It's called a solvation cage or a water cage, but you know that hydrogen has a permanent dipole, or the hydrogen-oxygen bond is permanent dipole. Hydrogen is partial positive. I know this video was a little bit longer than usual. Those are your 4 IMF, and again, go back and try to understand all the pink phrases, because those are the phrases that you need to be aware of to avoid any careless errors when assigning the types of intermolecular forces that a molecule has, and when predicting boiling points and melting points. Okay. I'm going to run a little bit over because I do want to show you one example. I looked this up. One example where I did have numbers for boiling point and melting point. So bear with me. Glycerol. Glycerol has this shape and constitution. You have three carbons, and each of those carbons has an O with an H. You should recognize that because of this OH bond, you have the ability to hydrogen bond. Okay, I'm just making sure that all the carbons have 4 bonds. The other molecule is called glycol, and actually it's called ethylene glycol. You don't need to know the names if you're in my class, but you do need to predict which one has the higher melting point and higher boiling point. Both molecules can participate in hydrogen bonding. The last pink phrase, the more hydrogen bonding, the higher the melting point and the boiling point. Higher the, we'll start with boiling point. No, we'll start with melting point. The higher the melting point and the boiling point. They will always go lockstep. If you're raising the melting point, you are also going to be raising the boiling point. Okay. This molecule, not only does it have more hydrogen bonding opportunities because it has 3 OHs versus 2 OHs for ethylene glycol, it's a bigger molecule. You know what that means? Remember this? As you increase the size, the number and or strength of the dispersion forces increases. So the bigger the molecule, the more dispersion forces as well. Look at the boiling points first. The boiling point for glycerol is 290 degrees C. For ethylene glycol, it drops 100 degrees to 197. And that's predicted because this has more hydrogen bonding and it has more dispersion forces. And also it has more dipole-dipole interactions because you have more carbons. Look at the melting point. The melting point should also be higher for glycerol. And the melting point for glycerol is 17.8 degrees C. And for ethylene glycol, it's actually negative 12.9 degrees C. So again, you have higher and higher. Okay, I'll let you ponder this video on your own and do your practice problems from the textbook and from your professor.